Okay, let's look at units of concentration. How much solute can be dissolved in that liquid? What are the units of concentration? And as we said, molarity is the first one we looked at, the moles of solute per liters of solution. Now, molarity is nice. It works very, very nicely for many calculations. But molarity has a problem. Recall from Gen Chem 1. If we were making a solution, and remember we had a volumetric flask here with our line across there, and we said, okay, we need to make this solution, and we added our solute into the top, whatever that solid was, we put it in there, and it's sitting in there. And then the question is, how much water do we add? Say this was a 100 milliliter volumetric flask. How much water do you add to dissolve up all that solid you put in there? And the answer wasn't very satisfying. The answer was enough. You add enough water. And the question was, well, why don't you add 100 milliliters of water into this flask? Well, because there's already solid in the flask, and that solid's going to occupy a volume. So if you add 100 milliliters of water into this flask, the final volume of solution won't be 100 milliliters, right? Molarity is moles of solute per liters of entire solution. And so how much water do you have to add? You have to add enough water to give you 100 milliliters of solution. Well, some people didn't like that. It works very nicely for calculations, stoichiometry problems, it works really nicely, but some people don't like that answer, so they came up with a new unit of concentration, molality. Recall, molarity is a capital M, molality, little m. That will be the moles of solute per kilograms of solvent. And while that looks a little hairy, what, kilograms of solvent? You have to weigh out your solvent? Technically, yes. However, recall, what is the density of water? Well, recall the density of water, to nice 2 to 3 sig figs, is 1.00 grams of water per 1.00 milliliters of water. The density of water is 1 gram per milliliter. Which means if you had 100 milliliters of water, that would be 100 grams of water. 1,000 milliliters of water would be 1,000 grams of water. Well, 1,000 grams of water is 1 kilogram. So 1 kilogram of water is 1 liter of water. A kilogram of water is a liter of water. And since we're mainly using water as our solvent in this class, realize molality is really just moles of solute per liter of water. Note, that is different than moles of solute per liters of solution. Liters of solution, you have to add enough water to get 100 milliliters. If you're doing moles of solute per liters of solvent or kilograms of solvent, you would measure out 100 milliliters of water and then add your solid to it. The final volume would be messed up. The final volume would not be 100 milliliters, but if your units are molality, we don't care. All right. So, for example, summing all that up, if you wanted to make 1 molar, 1 liter of 1 molar sodium chloride, you'd add enough water to 1 mole of sodium chloride to give 1 liter solution. If you wanted to make 1 molal sodium chloride, instead of molarity, we're using molality, 1 molal sodium chloride, you'd have added 1 mole sodium chloride to 1,000 milliliters of water, 1 kilogram of water. All right. And hopefully you remember this term. Hopefully it was discussed in the gases chapter when we're discussing Dalton's law of partial pressure. Remember, there's a term mole fraction. It is a concentration term. The mole fraction, X, of gas A. Say you had a number of gases mixed together. That's how we're looking at it before, a number of gases mixed together. We could take the number of moles of gas A divided by the total number of moles of gas, A plus B plus C, however you want to do it. The moles of the individual gas divided by the total number of moles of gas in your mixture. And that's when we were dealing with the gas laws chapter and partial pressures. Mole fraction is not limited to gases. You can have a mixture, a solution of various things, various liquids, or solids dissolved in the liquids, and you can still get the mole fraction of everything dissolved. For example, a nice quick example, if you had a mixture of 1 mole of CH3CH2OH, this is ethanol, 3 moles of CH3, C double bond O, CH3, this is acetone, and 10 moles of water. All it turns out, methanol is polar, acetone is polar, water is polar. They are all miscible in each other. They completely dissolve in each other. So this gives us a homogeneous solution. What is the mole fraction of acetone? Well, we've got 3 moles of acetone, we've got 10, 13, 14 total moles of molecules, so the mole fraction is our 3 moles of acetone divided by our 14 moles. Total is 0.214. Recall, mole fraction has no units. Note, that is very easy mole fraction, but what if an instructor were to do something crazy, like instead of giving you the number of moles of each thing, gave you the number of grams of everything? What if I had grams of ethanol, grams of acetone, grams of water, and asked for the mole fraction of acetone? Hopefully you'll see, oh, when I'm given grams of each, I'd have to divide each by its molar mass to get the moles, and then do the mole fraction that way. Remember, if given grams of anything, usually the first thing you're going to do is convert it to moles. All right. Another unit of concentration is weight percent. And just like mole fraction was the fraction of the number of moles of one thing divided by the total number of moles, weight percent is the mass of something divided by the total mass if you had. If you had the mass of A divided by the mass of A plus mass B plus C, the mass of the one thing you're looking at divided by the total mass of everything you have, you get the weight percent or mass percent. Weight percent is kind of the old school name for it, and mass percent is the better name for it. And realize that percent means parts per 100. So this weight percent, you have to multiply the mass of A divided by the total masses times 100 to give us 100%, parts per 100. So here's a question. What is the weight percent of acetone in the above solution? Well, we'd have to get to the masses of everything to figure that out. But we can do that. We were given 1 mole of methanol. We have to determine how many grams that would be. Well, recall that 1 mole would equal X number of grams divided by the molar mass of ethanol, 46.08 grams per mole. And so if we had 1 mole of it, that would be 46.08 grams. 3 moles of acetone, do a little math, would give us 174.3 grams of acetone. 10 moles of water, well, 10 moles times the grams over the molar mass gives us 180.2 grams of water. So we can convert our moles into grams and then get the weight percent or the mass percent, our 174.3 grams of acetone divided by the total mass that we have, 400, is 43.5% in terms of mass percent. Okay. Now it turns out that when you have extremely dilute solutions, where there's not much solute dissolved in the solvent, molarity just doesn't do it for us, because we get numbers like, oh, what's the concentration of the solution molarity? It's 0.00002%. Well, that's a lot of 0.00002. That's a lot of O's. It's tough to keep track of that, because like, what's the difference between 0.00001 and 0.00002? And you're like, well, that's not a whole lot of difference. Well, actually, that second number, 0.00002, is twice the amount as 0.00001. Therefore, when we have super dilute solutions, in order to keep it in our head and make the numbers more relevant to us, we have a new unit of concentration, parts per million. Now, the good news is parts per million is very easy to calculate. It was just like percent. Recall, percent is parts per hundred. Recall, we took our mass of our first thing, our mass of the thing we're interested in, our acetone, divided by the total mass, and for parts per hundred, we multiplied it by 100. For parts per million, we do the same thing, except we're going to multiply by 1,000,000 instead of 100. All right. But just some things to know, get the idea in your head about the parts per million to make it a little bit more meaningful for you, hopefully. So, 1 part per million would mean if we had 1,000,000 grams of a sample, 1 gram of it would be our solute, or the thing we're interested in. If we had something, we said, what's the concentration of it? 1 parts per million, which means if we had 1,000,000 grams of sample, only 1 gram of it would be the substance we're interested in. Now, doing a little math, that means also that if we had 1 milligram of the substance in 1 kilogram of sample, that is also parts per million. And recall, because when you're dealing with water, 1 kilogram of water is essentially 1 liter of water. That means 1 part per million would be 1 milligram of the substance in 1 liter of water. You've used the balances, I'm sure. 1 milligram is a very tiny amount. 1 liter of water is a fairly decent amount of water. So put 1 little milligram of a substance in a whole liter of water, and that would be 1 part per million. So parts per million and milligrams per liter are approximately equivalent. However, there are some things that we really don't want in water, some things that are even less concentrated than that. And so instead of parts per million, there's another term, parts per billion, ppb, parts per billion. And you calculate parts per billion the same way you did up here. You just take the thing you're interested in, the mass of what you're interested in, divided by the total mass. And when you multiplied it by 100, that gave you percent, parts per 100. If you'd have multiplied it by 1,000,000, that gives part per million. If instead you multiplied by 1,000,000,000, that would give you parts per billion. And parts per billion is a very low concentration, but that's what we want. If you work for a water lab that examines the water of the city or the town you live in, how much lead do you want in your drinking water? I bet the answer is none at all. Well, none at all is very hard to do, but you want the lowest amount of lead possible. So the amount of lead that's allowed in drinking water is something like 10 parts per billion, a very tiny amount of lead allowed in your drinking water. By the way, your book, the Tro book on page 595 has a nice table that goes through parts per million, parts per billion, and all of these percents. And they even have another one, a volume percent in there, something to look at. Okay, that's nice for this video. The next one, we'll start looking at those colligative properties, the properties of solutions that don't have to do with what's dissolved in the solution, just how much is dissolved.